gonna get started. Okay, so just an announcement. I do not have office hours tomorrow. Those are canceled because I'm starting my break early. I am sitting on a pretty large pile of emails that I am planning on responding to tomorrow. So if you wanted to catch me during office hours tomorrow, please do email me, and I am hopeful that I'll get back to everybody tomorrow. But yeah, obviously exam 2, those scores were just released. I believe questions for that will come out on Thursday. My biggest recommendation for improving scores is, first step, go back and look at the exams, like get yourself a treat and sit down and look over your mistakes and try and figure out what you got wrong and why. And that'll be doable on Thursday once those are released. Just as like a heads up, exam 3 I think is gonna feel like it's coming at you really soon. So obviously this Friday is off. The following Friday you have a recitation, and then the next Friday is exam 3. So it comes really fast. So yes, find some time to take a break and some self-care over the break, but also be aware that the pace doesn't slow down. Questions, or do you just need a second to complain about how fast things are happening? Give you guys a second to accept that. All right, so are there any questions on logistics other than just like complaints? Yeah. Old lectures? Oh, like to get forward on the content? Yes, I can do that. Yeah. So if you would like to spend some of your time over fall break, I can post old lectures, and I'm just gonna write this down so that you could get ahead if you wanted to. Not required. All right. Okay. Now we bring the convos down. We have 2 sections from chapter 16 to wrap up, and then we head into chapter 17. It is all still acid-base. Please, if you are talking, turn that off. Okay, it's all still acid-base stuff, but now we're going to look at some slightly different systems. So our first twist is that we're going to look at properties of salt solutions. So what I'm asking now is, will a salt solution change the pH of the solution? Will it make it an acid or a base? Okay, so if a salt is water soluble, it dissolves into its component ions. We talked about that a lot in chapter 13, but we didn't ask ourselves if those ions could impact the pH. And now we're going to ask that question. All right, so some of these ions will then undergo hydrolysis reactions. When I say that, all I'm saying is that they're going to react with water to generate some H plus or OH minus. If you do one of those, if you make some H plus or some OH minus, you are changing the pH. Okay? So quantitatively, these questions are no different than the weak acid, weak base questions we just did. You just need to see them that way. Okay, so just generically, I'm saying we've got some salt. Okay, this is our generic salt. Okay, so this is our cation, and this is our anion. When it goes into solution, we'll get M plus and X minus. We're wondering if these are reactive. Okay, so are these reactive with water? Okay, and if they are, then they're going to be producing H plus or OH minus. Okay, so that's how we frame this. I'm going to split it up. We're going to start by looking at the anions that will have an impact on pH, and then we'll look at the cations. All right, so let's focus in on X minus. So these anions that go into solution. Okay, And I pulled this graphic because we've already talked about this. Okay? We said at the end of our, well, actually throughout all of 16 so far, we commented that the conjugate base of a weak acid is a weak base. Okay, so let's highlight some of these that I want to pick out. Okay, so if I put H3PO4 into solution and we get its conjugate base, that H2PO4 minus, that's a weak base. Okay, so if I put that into solution, it will act as a base. It'll generate OH minus. Okay, if I want to add that to solution, I don't just have a jar of H2PO4 minus sitting in lab. I cannot cram only negative charges next to each other. If I had that in lab, it would be balanced by a cation. So it would be like H2PO4. That would be a salt, that if I added it, it would make my solution basic. So all of these are examples of anions that if I put them in solution will act as weak bases. Okay, so I'm highlighting. I really want to focus in on these over here. And I didn't grab HSO4 minus, but I could have. Ah. There we go. Okay, I would include that one up there as well. So if I wanted to add, F minus to my solution, right? Which we, hopefully at this point, you're like, okay, F minus, that's a weak base. It's the conjugate base of a weak acid. Therefore, it will function as a weak base. If I wanted to add that, it must be added as a salt, right? So I wouldn't say, hey, I added F minus. I'd say I added NaF. I'd added sodium fluoride. So for example, NaF. So if you see a salt where the anion is the conjugate base of a weak acid, you know that's going to produce a basic solution. And there's one caveat which we'll get to in a second. Okay? So any of those that I circled, and I guess let me actually circle SO4 2 minus in there too, these will all potentially make a basic solution. Okay? And it's these amphiprotic ones that we got to call out. So I'm gonna highlight some of them. I'm gonna star the ones that we need to talk about later. Okay. Okay. All right. So what anions? These are our reactive anions. These are the reactive ones. All right, so the question is, well, how do you remember that these are the reactive anions? Well, I'll tell you that you should know the unreactive anions, all right? So it's the folks up here. If you are an anion and you are produced by a strong acid releasing its H+, you're a negligible base. So if the anion is one of those 6, and then I put in parentheses 7, because I'm also actually going to include HSO4 minus, so the conjugate base of sulfuric acid. If you're one of those anions, these are unreactive. They're not going to produce OH. Don't produce OH minus because in this reaction, they don't take a proton. Okay, so let's look at, we'll highlight Cl minus. So if I put Cl minus into solution, right, and I add it to I put it in with some water, okay, and I'm like, oh, maybe I'll make some HCl and some OH minus. You look at that and say, no, I'm not going to make HCl, because as soon as HCl goes into solution, it splits up. So this doesn't happen. Okay? So if you can remember those, now you've got your list of the anions that don't react. Okay? So I'd say unreactive, see I missed an I there, anion. And then I'm going to star this one too because we'll have to talk about this one later. Along with those phosphates. Okay. All right. So these are the ones to recognize. So let's try, I have another example here. So this is washing soda, so Na2CO3. When I put Na2CO3 into solution, it's soluble in water, so it splits up into 2 Na+, and the CO3 minus. Okay, so in here I would also have 2 Na+, but we're going to call those spectator ions because they don't do anything. All right, so when I look at this, I say, oh, that splits up into the 3 ions, 2 Na+, and CO3 2 minus, the carbonate. Okay, and then I know that right, that is the conjugate base of HCO3 minus, right? So this is a conjugate base of a weak acid. Therefore, it must behave as a weak base. So I should look at it as taking a proton from water. It'll generate some OH minus, and it'll make this a basic solution. Okay, so I want you now to write the reaction, or write what happens when potassium formate, so KHCOO is added to water. Okay, so take a stab at that. What are the component ions? So you're going to have a cation and an anion. Look at that anion, ask yourself what it is, what acid is it related to, and then write what it will do in water. All right, so my first step looking at this on the exam, I'd look at that and say, okay, well, I know potassium, that's a group 1 metal, so it's going to form K+. So then my HCOO must be minus, just a minus charge. That's my formate anion. It is the conjugate base of formic acid, which is HCOOH. That is obviously not one of our strong acids. It must be a weak acid. Therefore, HCOO minus is a weak base. So when I put it into water, it will establish a dynamic equilibrium where it pulls a proton from water. We make a little bit of HCOOH and some OH minus. That changes my pH, right? That's going to increase pH. So we'll have a basic solution. All right? So you will get sort of conceptual questions like this. Hey, I added potassium formate. Is it going to be acidic, neutral, or basic? Okay? So you're going to have to assess for different salts, what will it do to the pH? and it'll be like probably a drop down where we give you those 3 options. Or we could give you a quantitative question. We say, hey, we made this concentration, let's calculate the pH. Okay? Yeah. Because remember, well, an increase in pH means that we have more OH minus than H plus. So if I'm making OH minus, I'm increasing the pH. Remember, pH greater than 7 is basic. pH less than 7 is acidic. Acidic. Yes. But I'm not putting in H plus, I'm putting in OH. I'm generating OH minus with this reaction. A basic solution. Yes. Yes. Yep. Okay, so anions generally, we're going to have a general rule. Anions, so reactive anions generally make basic solutions. Okay. Again, I've been starring some because that's not always true, but generally it's true. We have a couple exceptions to the rule. All right, so let's look at a quantitative problem. All right, so what is the pH of a 0.050 molar solution of NaNO2? And I give you the pKa of HNO2. All right, so that's an acid, but I haven't added the acid. Okay, so I'd break this down. If I got this question on the exam, again, I would look at this and say, what does that make when it goes into solution? What are the component ions? So NaNO2, when I put it into water, I'm going to get Na plus and NO2 minus. Okay? That must be a weak base. Its conjugate acid, okay, so let's look at its conjugate acid, is HNO2. We know that it's not a strong acid because it's not one of our 6. It's not one of the 6 monoprotics. Also, you're given a pKa for it, which is another way of us telling you that it's a weak acid, right? Quantitatively, if it's a weak acid, we have to tell you what its Ka is. All right, but I didn't add that. Okay, what I added was the NO2 minus. So when that goes into solution, we're going to write it pulling off a proton from H2O. So we'll get a little bit of that HNO2 and some OH minus. So this should be a basic solution. All right, and this is now just a weak base question, except for that the weak base was in a salt. It was packaged and delivered with a cation. Okay, so we're going to write our standard ice table. We don't care about our H2O. We're saying we don't start with any of those components. I'm going to lose a little bit of this. I'm going to gain a little bit of these two. So at equilibrium, these are my values. So I need to set this up. This is the K. I'm going to use that equation for my Kb. So I'm going to put my products on top. Now I need to know what that's equal to. Okay? And that's where this piece comes in, that we know that there's a quantitative connection between the Ka or the pKa of an acid and its conjugate base. So remember that pKa plus pKb at room temperature equals 14. Okay? So my pKb equals 14 minus 3.15, which I don't think I did it this way in my notes. You never trust mental math when you're in front of a bunch of people. Okay, so my Kb, remember that P in all of these instances just means the negative log. Okay, so pKb is the negative log of Kb. I need Kb, so I'm going to solve out for that. Kb equals 10 to the negative 10.85. That gave me, just make sure that this is consistent, 1.41 times 10 to the negative 11. So it's a really weak base. That's a pretty small number, but it's still going to produce a little bit of OH minus. All right? So there's my Kb expression. I'm going to grab my equilibrium values. Because Kb is so insanely small, remember 10 to the minus 11th is a very small number, I'm going to guess that x, the change, is also small. So I'm going to make our 5% assumption and call this just 0.05. So I'll have x squared over 0.05 equals 1.41 times 10 to the negative 11th. I solve for x. I do indeed get a very small number. It's 8.4 times 10 to the negative 7th. That is much less than 5% of 0.05, so we've passed that assumption test. This is, as a reminder, we've solved for our OH minus concentration. The question is looking for pH, so our final step is to relate that to pH. And I got 7.92. All right, and then at the end of the question, especially if it was a numerical, I stop and I ask myself, does that number make sense? Okay, it's slightly basic. It's a little bit above 7, not very much, which kind of jives with the fact that my Kb is a really, really small number. This is a very weak base. Okay, so I shouldn't see a huge increase, but I did see a little bit, it's a little bit basic. So that all makes sense. Okay? Quantitatively, these are no different than the problems we did for weak acids and bases. The key here is to recognize and ask yourself successfully, answer the question, what is that? What does that do in solution? Okay? All right. So that is our reactive anion that makes the solution basic. Now, why have I been starring some of these anions as like little weirdos that do something different? And you may have noticed I was starring anions that also had H's, that still had a proton. In other words, they were amphiprotic. They could do both. So for example, we're going to start off with a sodium bisulfite. Okay, that splits up into Na plus and HSO3 minus. Okay, you look at that and say, hey, HSO3 minus, that has a negative charge on it. It's carrying some extra lone pairs that in theory could go grab a proton, which would mean it acts as a base. Or, hey, it still has a proton to give. So it could generate H+. So it can also act as an acid. That's why I called it amphiprotic. It can do both. So for an anion like this, I have to ask myself, which one would it rather do? Would it rather behave as a base or as an acid? All right, so we need to write out what that looks like. I did acid on top, but let's do base here. Okay, so a Bronsted-Lowry base takes a proton. So in this case, it's going to grab a proton from water. We'll make H2SO3 plus OH minus. Okay, there it's acting as a base. I'm going to generate some OH minus. My pH increases. Or, I notice it still has that proton. It could donate that proton. So it could be SO3 2 minus and H3O plus. How do I assess which one it does? Okay, for that, I will need to know there's a Kb associated with this process and a Ka associated with that process. You can't do this question without those numbers, okay? So I need to give you those numbers in some way, and then you compare, is Ka greater than Kb? Then the solution is acidic. Or is Ka smaller than Kb, in which case it would be basic. So we have to know those two numbers. Yeah, Anna. No. You have to have the numbers. There might be some quantitative work on your end once I give you the numbers, but I need to give you some numbers to start with. So we're gonna look at that example now. Now with the numbers. Okay, so here I've taken this content and I've just written it on the next slide in a nice way. Okay, so here's HSO3 minus acting as an acid. Here it is acting as a base. Still don't know what I'm doing in PowerPoint. All right, and here it is. It says that there's no HDMI signal, which I vehemently disagree with. There we go. All right, here it is acting as a base. Those are the two reactions that we just wrote before. What you would get in addition to that question is the table above. All right, so notice that the sort of parent acid of HSO3 minus is sulfurous. When it's fully protonated, there's H2SO3. There's two protons that can come off, so we've got Ka1 and Ka2, so it's a polyprotic. All right, this Ka1 is to describe the likelihood of H2SO3 losing a proton, the first proton. Ka2 is the likelihood of HSO3 minus losing a proton. All right? So when HSO3 minus acts as an acid, that is just the reaction for Ka2. Okay? This is described by Ka2. There is HSO3 minus. It's giving away its proton. That is what Ka2 describes. I know that number. It's in the table. It's 6.4 times 10 to the negative 8th. The base part is where this, I think, feels a little bit trickier. All right, so as a base, here's HSO3 minus. If I want to know the Kb from these Kas, we need to say Kb equals Kw divided by Ka, where Ka is the conjugate acid of HSO3 minus. And we know that. We wrote it out in our base reaction. The conjugate acid of HSO3 minus is H2SO3. So if I want to calculate the Kb of HSO3 minus, I actually will tend to call this Kb1 because it will be Kw divided by Ka1. That's 10 to the minus 14th divided by 1.7 times 10 to the negative 2. So Kb1 equals 5.9 times 10 to the negative 13th. Now we have the two values that we need to answer this question of is it going to be basic or acidic? Because I'm comparing these two, and I see, oh, HSO3 minus is much more likely to behave as an acid than as a base, because 10 to the minus 8th is a larger number than 10 to the negative 13th. So this is going to be, so Ka2 is greater than Kb1, therefore this is an acidic solution. So this is the caveat, this is the nuance, the exception. I put an anion into solution, and most of the time, if you're a normal non-amphiprotic anion, it will make a basic solution. But this one made an acidic solution because it was amphiprotic. All right, let's see if any of that sunk in. Now I'm going to give you your own practice problem. Predict whether the salt Na2HPO4 makes an acidic or basic solution when it's dissolved in water. So notice that this is HPO4 2 minus. I give you the table for its like parent polyprotic, H3PO4. You have K1, K2, K3. So you can use the same process that we just used for sulfurous to do this question. So write out what ions do you have. You'll recognize that the anion is amphiprotic. Write it out as an acid, write it out as a base, and then compare those values. You need to write it out as an acid and a base. And then you'll find a Ka and a Kb, and you're going to compare their magnitude. Okay, let's look at it together. So you see this question, and you're like, okay, even if I didn't write salts, you're like, there's some metals, and it's stuck on to something that, like a polyatomic anion. I should write out what this does in solution. It splits up, it dissolves as 2Na plus and HPO4 2 minus. Okay, so that's a good first step is to remember that sodium, a group 1 metal, each of them will be charged +1. And so if there's 2 of them, then my anion better be -2 because it got to have a neutral salt. Okay, so now I'm looking at this HPO4 2 minus. Is it amphiprotic? The answer is yes. Okay, so an anion, right, something that's negatively charged, has the capacity to take a proton. It's somewhere on it, it's got some extra electrons that it could use to make a bond with an H plus somewhere. So it can act as a base. It can also act as an acid because there is still a proton left there. You also know that that last one can act as a proton because we give you a Ka for the third proton. So this was for the first proton coming off. Here's the second proton being removed. And here is the third proton coming off. So that's what we are dealing with, okay, when it acts as an acid. All right, so let's write it out. As an acid, it donates a proton. So I'll have HPO4 2 minus plus H2O in equilibrium with some PO4 3 minus and some H3O plus. So this is described with Ka3. What's the likelihood of that third proton coming off? And now we say, well, it could also act as a base. All right, and we remember that bases accept protons, they take them. So it will grab a proton and form H2PO4 minus and OH minus. All right, I want the Kb for this. But I don't have Kb's. I didn't give you Kb's, I gave you Ka's. So I find the conjugate acid. The conjugate acid is H2PO4 minus. I need its Ka. That's Ka2. So the Kb, I will also call this Kb2, is Kw divided by Ka2. That's 10 to the minus 14th divided by 6.2 times 10 to the negative 8th. That is 1.6 times 10 to the negative 7th. That is a bigger number than 10 to the minus 13th. So in this case, Kb is greater than Ka, and this salt solution would be basic. Yeah. So in the table, what I would do is as you go Ka1, so I'd say that's fully protonated. That's the first one being pulled off. So I'd write out H3PO4. And then for Ka2, oops, and that was actually the negative sign, then I'd take one proton off and I'd write what's left. So Ka2 is for H2PO4 minus, that next proton being pulled off. That's not what I've added. I added HPO4 2 minus. That is the third and final proton to come off. So that should be this Ka3. So this is like the first deprotonization, the second deprotonization, and here's the third one. So what we've put in here is this is our last proton to come off. So I'm going to take the last Ka value. Does that feel comfy? Yeah.
So we have like -2 is our final, so that's why I took Ka. But it won't always be like constant. The first proton being pulled off, like say our final is -4 and 1. That's assuming, like this is assuming that's a fully charged.
Right. So in the table, we'll either give you like, hey, this is the Ka for that, or we'll give you a table like this, and then you can assume like that first number is pulling out the first one, the second one's pulling out the second, the third one's pulling out the third.
It doesn't have to be like a fully, it doesn't have to be constant for Ka4, right? Because like you see how it's like there's no charge for
the acids that we usually start with are going to be fully protonated. Neutral, yeah. And then you keep pulling them off, yeah. Okay, so that was our nuance. That's why if you go back and look at the species that I starred, they all were amphiprotic, okay? That's why you had to give them a little nuance and say they fall into this weird category where they could act as a base or an acid. Okay, so that wraps up our anion activity. All right, now we turn to the cations. What will the cations do? Okay, so again, I originally wrote it out like this. Here's our generic salt. All right, turn down the side convos. We're going to have M plus and X minus. Okay, we're now asking ourselves, what will this do? All right, so when that's reactive, and there's times when it's reactive and times when it's unreactive. When it's reactive, what will it do? So we're going to focus on the reactive cations. Okay, and there's two categories. All right, they are the conjugate acids of weak bases. That's one category. Okay, so notice that if I looked at the conjugate bases of these, that would be NH3 and CH3NH2. So remember, one of our primary categories of weak base were neutral nitrogen compounds. Those are our weak bases. If they grab a proton, they become the conjugate acid. Those are weak acids. Okay? So if I use them as the cation in one of my salts, okay, so for example, if I have some ammonium, I don't just have this sitting by itself in a jar on the table because they will repel. I have to partner that with an anion. So for example, I might have ammonium chloride. If I put that into solution, I get NH4 plus and Cl minus. This then goes on to produce, well, let's actually draw it out. It will do this with water. It'll hand over sometimes its extra proton. And we'll wind up with an acidic solution. Okay? So, cations, if they're reactive, we don't have exceptions to this rule, which is nice. Reactive cations will produce an acidic solution. Okay? So let's write that. Reactive cations make an acidic solution. All right, so one of the main categories, we've got two of them, are these protonated weak bases, weak nitrogen bases. Okay, so like NH4 plus and then CH3, NH3 plus, something where I've added a proton to that weak base. Okay, the other category, okay, we make this observation, okay? Solutions of iron 3 nitrate are acidic. Question is why? Okay, and we think about that salt splitting up into its components. I'm going to have Fe3 plus and 3 nitrates. Nitrates don't do anything in solution, right? If anything, you might posit that they make it basic, but these are the conjugate, and I'll put this in parentheses, they're not conjugate bases, they're negligible of a strong acid. They don't do anything. This acidity has to come from Fe3 plus. So how do we understand the chemistry of Fe3 plus making a solution acidic? All right, so let's expand this out. I know your favorite term, Fe3 plus, is a Lewis acid. Okay, it is electron poor. Loves to accept electrons. All right, so when you put it into water, water will act as a Lewis base and donate some of its electrons to that cation, right? So in general, like large charges like a 3 plus are not happy. They need to be stabilized, right? There's a lot of extra positive charge in there, and we know that putting positive charges next to each other is repulsive. So we're going to want to balance that out. We want to stabilize it. That happens with water. And I think the image on the next slide will do a much better job than this like big old reaction. But what we're reading here is that when I put Fe3 plus into solution, water will form a complex around it. Okay, so all of these 6 waters are circling around that iron and stabilizing it. They're donating some electron density to that Fe3 plus. So much so that one of these really puts in some electron density. And then another water is like, oh, you don't want this? Like, you're giving some electron density here. Let me take this for you so you have extra. Okay? And that means that this will shoot off into solution as H3O+, and that means an acidic solution is forming. So there's our H3O+. So if my scribbling wasn't sufficient for you to see this, here is the book diagram of what's happening. So here's our Fe3 plus in the middle. Okay, there's our, it is 6, right? 1, 2, 3, 4, 5, 6. Our 6 waters circling around it. All of the oxygens are pointing inward. Another water comes along and takes a proton so that there's more electron density given to the iron. So it goes from a 3+ complex down to a 2+ complex, which means that an extra proton has been pulled off, and we start generating H3O+. Okay? The quantitative bit that you guys need to know is that it's so acidic, Fe3+ is so acidic that we can assign it a Ka value. So I put in Fe3+, and that will have an acid dissociation constant of 6.3 times 10 to the negative third, which is a small number, but on the scale of Kas is actually quite a large Ka. So this turns out to be a pretty acidic solution. Okay? More importantly, I need you to recognize the trend of which metal cations produce acidic solutions. It's not all of them. Okay? Here are the cations that if you put them into solution, which remember, if I'm going to put a cation into solution, it had to come in as a salt. I don't have a jar of Fe3+. I have to have an anion balancing it. So that comes in as like FeCl3 or iron nitrate, whatever. Okay? But here, all of these have meaningful Ka values. So if I put in any of those cations, they will produce an acidic solution. All right? So let's point out which cations don't produce an acidic solution, all right, and why. So here I've just gone into a little bit of depth on why this is. If you look at the charge density, so that's the charge value, so in iron 3+, that would be 3, and then I divide it by what I really should write as the ionic radius, okay, to see how much charge do we have in a little space. And what we notice about the reactive cations, the ones that produce really acidic solutions, is that they have a very high charge density. So they are very likely to draw in those electrons from water, which means that a proton gets pulled off. Okay? What the comparison is look at how big these numbers are in comparison to our group 1 and 2 metals. Okay, so Na+, potassium+, calcium 2+, magnesium 2+, all have pretty low, relatively speaking, charge densities. So these will be solvated. Water does come around those and form a solvation shell. But it doesn't need to be stabilized in the same way as these transition metals, okay? And these are really, because they're really big, and so that's not as stable. We're putting a bunch of positive charge into a tiny space. That should raise red flags in your head, but that's not electrostatically stable. So we do something. The system does something to fix that, okay? So we'll notice that these group 1 and 2 don't. They're unreactive. These are our unreactive cations. Okay? These are the metals that are usually used if we want to make a basic solution, right? If I want to pair a cation with OH minus, and my intent is to make the solution basic, I wouldn't want to pair it with a metal that's going to make it acidic, right? I wouldn't, if my intent is to just drop the pH, I shouldn't add in iron hydroxide because my iron would be raising the H+ concentration while OH minus is lowering it. So these are the ones that we usually find if we're trying to make a basic solution. All right, visually, I think this is helpful. These are the folks that we talk about as reactive metals. And then if you're over in this corner, these are our unreactive or non-reactive. All right? So that's our second category of cations that are reactive, and they also lead to acidic solutions. All right? So we're going to do a big summary slide of all these different salt solutions. Okay? So what have we learned? Okay, I'm going to split this up into 4 quadrants. All right? If we have unreactive cations, so that would be your group 1 and 2 metal cations, like Na plus or calcium 2 plus. Okay, and I pair that with an unreactive anion. So those are our conjugate bases of strong acids. Right, so that would be your Cl minus, your Br minus, I minus. Okay, if you have a salt made with one of those cations and one of those anions, then there's no change. This should be a neutral solution. Okay, neither of those ions does anything. They're not reactive. They don't undergo a hydrolysis reaction. Okay, so let's go down and we'll do reactive cations down in this bottom left. So if I put in a reactive cation, that would mean a conjugate acid of a weak base. So an example would be NH4 plus, or a densely charged metal cation. Examples of that would be Fe3 plus, aluminum 3 plus, so on. Okay, so one of those reactive cations, but then I pair it with an unreactive anion. We've already identified those, our conjugate bases of strong acids. These will always produce acidic solutions. Okay, so a reactive cation, but an unreactive anion will always produce an acidic solution. Okay, let's go to the top right. Now we're going to leave it as an unreactive cation. So one of our group 1, 2 metal cations. And then we're going to add a reactive anion. Okay, so we have 2 different types of reactive anions. We have 1, the conjugate bases of weak acids that are not amphiprotic. Okay, so that's like our NO2 minus, our F minus, the HCOO minus. Those are all conjugate bases of weak acids, and that's going to produce a basic solution. And then we have our caveat, our exception, that if it's amphiprotic, so examples would be HSO3 minus, HCO3 minus, then we have to compare Ka and Kb. So you need numbers to do that kind of question. Okay, that could be basic or acidic, but you can't answer it unless you know those Ka and Kb's. And then we have our bottom right where they're both reactive. And a reactive anion. And we'll say it depends. So like you probably, okay, let's say, I know for certain, you won't see this question alone. Okay, I can't give you a reactive cation and a reactive anion and say, hey, is it acidic or basic? I haven't prepped you for that. What I could ask you is, like, in comparison to another salt that only has a reactive cation or only has a reactive anion, then you could do a comparison, but we generally avoid these where both of them are reactive. Okay? So you're just like, probably you're going to be in one of those other 3 categories. All right? So get those down, and then on the next slide, you can test how much you've absorbed. Here are 5 different salt solutions. This is a type of question that you will get on the exam. There will be a drop-down menu associated with each of these salts. You will pick acidic, basic, or neutral. All right? Let's take 2 minutes. Do this with somebody next to you. Go back to the slide, the prior. Identify, write out the cation, write out the anion. Find where they live in those 3 buckets. Okay? All right. I've got numbers now. So if you think it's acidic, a 1, neutral 2, basic 3, sodium nitrate, 1, 2, or 3. Lovely. I would guess this is neutral. That's Ne plus and NO3 minus. Look at the cation. That's a group 1 or group 2. It's not densely charged. I don't think it's going to like draw in the waters so tightly that a proton will get pulled off. So that's unreactive. NO3 minus, that's the conjugate base of a strong acid. NO3 minus doesn't want a proton. It's really good at giving them away when it has one, but it doesn't take it back. Neither of those are reactive. So this is a neutral solution. All right, iron 3 nitrate, is that acidic, neutral, or basic? Good. That iron 3 plus is very densely charged. That was the actual example we looked at. That loves to draw in waters, so much so that one of the protons on waters gets acidic and it's yanked off. And we wind up with an acidic solution. And then for the same reason that we described in the first example, NO3 minus doesn't do anything. Okay, KNO2, is that acidic, neutral, or basic? Good. That is going to be basic. K plus, that's my group 1 metal, doesn't do anything. NO2 minus. You say, hey, the conjugate base of NO2 minus, the conjugate acid is HNO2. That's not a strong acid. It must be a weak acid. Therefore, NO2 minus is a weak base. So that's going to pull there's going to be a meaningful pulling of protons to make HNO2, which leaves OH minus behind. This is basic. All right. KBRO, acidic, neutral, or basic? Good. I have this one as basic for the same reason. BRO minus. See, what's the conjugate acid of that? BROH, okay, hypobromous. That is not a strong acid. It must be a weak acid, which means that its conjugate base has to be a weak base. Okay? That's also basic. It has a base that's a weak base, yes. All right, last one here. CH3NH3Cl, is that neutral, acidic, neutral, or basic? I love it. CH3NH3 plus. That's how I would write this out. The Cl minus doesn't want it. Okay, that is a reactive cation that will give away a proton. It's the conjugate acid of a weak base. That makes this an acidic solution. All right, you guys have lots of practice on these in your homework that I assigned for after this lecture. This undoubtedly will show up on your exam. Okay? And usually in this style where we ask you like the drop-down question. Okay, that was salts. Now we turn to the last little bit of chapter 16. We have been sidestepping this question all the way along. Why are some things acidic? Okay, what are the structural features of a molecule that means it's okay giving away an H+? We want to tie that behavior to structure. Right now we've just been saying, hey, here's Ka and Kb, don't ask me any more questions. Okay, now we want to tie it to the stability of the acid and the base. So what can we say about the stability of those two species? Okay, so we're going to look at some trends. Okay, so our first trend is that acid strength increases with bond polarity. So if we're going, remember that polarity is a measure of the difference in electronegativities. Okay, and this is for, well, I'm going to highlight, what am I? Yep. Binary acids. So where the H, where our proton is directly connected to the thing that we're changing, okay? So as we go across a row, right, our most electronegative element is fluorine. So as we go across, our bonds are getting more polar, right? They're getting more polar as we go towards fluorine, okay? So that means that our acidity should increase as we're going across the table. So this is like why HC bonds are almost, sorry, HC protons, let's call it HC protons. So I'm like talking about that guy right there, almost never acidic, right? Because this is a nonpolar bond, unless we're looking at some like really extreme molecules, okay? So this explains the trend as we go across a period. Okay. The other trend we observe for binary acids, okay, so for these HAs, is bond strength, okay? So the strength of an acid increases as bond strength decreases. Okay, so again, this is for a binary acid. So let's look at an example of this. I think the sort of key one here is that this explains why HF is a weak acid. Okay, HF has a pretty high bond strength. It's 567. As we go down, so when we look at HCl, it has a bond strength of 431. Okay, and so for HF to act as an acid, that bond has to break. So if it's a stronger bond, then it's less likely to happen. Okay, bond strength generally between like a proton, so hydrogen, and some other element, it goes down. So the bonds are less strong as we go down a group. Okay, so this is why HF is a weak acid, even though it has an incredibly polar bond, right? That is the most like polar H bond that we could have. Okay, but it's also a really strong bond in comparison to HCl. Yeah. So in this case, I think the best explanation is for the size of the atoms, and we have better overlap in our orbitals when they're about the same size. As we go down, we're having a much larger, it's like Cl, Bri, those are bigger atoms. We're going to have less optimal overlapping between our little tiny hydrogen. Okay. And then lastly, we want to think about the stability of the conjugate base, of the thing that we're leaving behind, right? So when an acid does what an acid does, it leaves behind A-. This question is, how stable is that? Okay, so some things we might think about, is there resonance? And we'll talk about resonance in a couple slides. How electronegative are the atoms? How, like, does that thing want a negative charge? Okay? How well can it stabilize it? Because again, these things happen, right? But it's generally not favorable to cram a bunch of negative charge into a small space. So we need to do something. The things that are really acidic are good at stabilizing that charge. So like Cl- turns out to be really good at stabilizing that charge, right? It gives the noble gas configuration. It's an electronegative element. It has a high electron affinity. It is good at doing that, okay? As we go down and across the table back towards the metal side, those things are less likely, they're less good at stabilizing a negative charge. Those are not good acids, okay? All right. So here is our summary for the binary acids, for HA. So really listen, someone makes a mistake every year. These rules are just for HA, where the proton is attached to the atom that we're changing. Okay? Just for HA. We're going to look at a different class in the next 3 slides, and somebody always mixes them up. Okay? So that means that we're going, as we go down and to the right, those are our strongest acids. Okay? Now, We're switching categories now. We're not talking about binary acids on the next couple slides. We're looking at oxyacids. Okay? In oxyacids, the proton is always attached to an oxygen. All right? And then there is another atom that is attached to the oxygen, and that's what we're changing. Okay, so importantly, we aren't going to use bond strength as an argument for acidity here, because the hydrogen is always attached to an oxygen. So bond strength doesn't play as big of a role here, because we always have an HO bond. It's about what is this, what is the identity of this, and are we pulling electron density or adding electron density? Okay, so the big key here is if we have the same number of oxygens, and we can have more than one, but we're going to look, if we're comparing across just the same number of oxygens, okay, more acidic means that Y is more electronegative. Okay, so this would be less acidic and more electropositive. So how do we understand that? Well, if I come in and I take this proton, right, it gives it away. These shared electrons are now shared between O and Y. If Y is really electronegative, it likes to take that extra electron density. It will stabilize A minus. Okay? If it's really electropositive, it doesn't do as good of a job. Okay? You could also imagine if this is really electronegative, it's already maybe taking some electron density from oxygen, which makes that proton even more electropositive to begin with. Okay? So that's one thing we could change in oxyacids. What is that oxygen attached to? And we see a very obvious trend here. So we're going down our sort of halogen series here. So ClOH, BROH, IOH, HOH. Okay? So these are the electronegativities of those Ys. Okay? So we see that as we are going down, as we're making it less electronegative, our Ka decreases. Okay? So HClO in this series where there's just one oxygen is our most acidic molecule. Okay? Because that's most electronegative. So this is probably best stabilized. That A minus, which in this case is OCl minus, that's probably most stable. Okay? Because that Cl can really help out stabilizing an extra pair of electrons. The other thing we can change, okay, so not just the Y, but we can also change the number of oxygens attached to that Y. Okay? And as we increase the number of oxygens, we increase the strength of the acid. Okay, so hypochlorous and chlorous, these are both weak acids, but by the time we've put on 3 and 4, those are now strong acids. Okay, so the argument for this is that we can spread out the negative charge over a larger number of atoms. Okay, so let's look at perchloric. And this is where we use resonance structures. Okay, I'm going to draw it out like this. Okay, and I could draw it in a couple different ways where I'm optimizing oxidation numbers. But let's say I come in, I pull off this proton. These shared electrons are then put onto that oxygen. Okay? And what's important about the added oxygens here is that now I can spread all of that electron density out across the other oxygens. There's nothing special about that one. Okay? Those electrons are really going to come, they might come down, and maybe they push up and they sit on this oxygen. Okay? So I could have a resonance structure that looks like this. And I could do that all the way around, right? And none of these are real. Like if I could shrink down, I would never find the electron pair like in one place or the other. It's smeared across, right? It's like cream cheese on a bagel. It's spread evenly around, which really stabilizes it, because now I'm not putting electrons in one spot and confining them. I'm sharing them around a bunch of electronegative elements. That sounds more stable, okay? So resonance stabilizes. Okay, so this is why we can understand like HNO3, HClO3, and HClO4. All of them have a number of resonance structures. So that negative charge gets smeared out, which is stable. All right? So, take a second. Compare these two. This is another very common structure for an acid, for like strength of acids on an exam. Okay? Compare these two. Which one is more acid, more acidic? Hold up a 1 if it's HBr, hold up an HF if it's HF. Which one's more acidic? Good. I mean, we all know this. HBr is one of the 6. If you haven't memorized it yet, please memorize it. That's a strong acid. This is a weak acid. All right, the argument that we would give for that, it's a weaker bond. All right, let's look at phosphane versus hydrogen sulfide. Which one is more acidic, 1 or 2? Good, I picked 2, okay? I'm looking at them, they're in the same row. Sulfur is going to be more electronegative, okay? These are both binary acids. The hydrogen is directly attached to that element that we're changing, and so I have a more polar bond in HS, okay? So I'm gonna pick H2S. All right, HNO2 or HNO3, which one's stronger? Good, I put more oxygens onto the nitrogen in HNO3. That means that when that proton's removed, there's more resonance. More oxygens on an oxyacid means a stronger acid, okay? More oxygens, therefore more resonance. Stabilization. All right, sulfurous versus selenous. Which one is the stronger acid, 1 or 2? Okay, this is the one to remember, that it's an oxyacid. The hydrogens we're asking about are not attached to sulfur and selenium. They're attached to the oxygen. And so for oxyacids, the trend is just which one has the more electronegative Y. Sulfur is more electronegative. So it's sulfurous. Okay, so Y in my oxyacid structure, they have the same number of oxygens. Okay, So all I'm asking, I'm looking for why. So sulfur is more, oh, and there's going to be another hydrogen here. If we want to be like accurate about it, S is more electronegative. That would be my justification. And this is an oxyacid question. Okay, you could confuse that. You could get that question wrong if you were applying the binary acid rules where you're also considering bond strength. That is the hiccup that people encounter. Okay? I'm going to talk about one more class of weak acids, and then we will be done for today. Carboxylic acids. We run into these all the time. Okay? Whether you've noticed it or not, we have shown you a bunch of weak acids where you see something attached to COOH. Okay? That's a carboxylic acid functionality group. When you take the proton off, it's COO minus. That is the carboxylate. So you get the 8 anion. All right, we talked about the formate anion, the acetate anion. Those are just carboxylic acids with a proton removed. These are good acids because of resonance and because this is a polar bond between our oxygen and hydrogen. When I take a proton from this, what happens? I'm left with this structure. Well, that negative charge doesn't just sit on that oxygen. It shifts over and it shares it. We've got a smear of electron density across the whole thing. Okay, that's why that structure, that COOH, you look at it and you say, oh, that's a weak acid. Okay, that is like and you'll see this a ton in biochemistry. COOHs are all pop up all over the place. It's like on amino acids. You see that and you're like, oh, acid. And you know why? Because I can share it in this resonance structure. Okay, and that's like really what I should draw as this. I can put it on either side, okay? It's not that one of them is special. I'm going to say one more thing. I can make this carboxylic acid more acidic, okay, if I put more electronegative things out here. So if I were to switch all of these to F3, that's trifluoroacetic acid, then that would have a Ka value of 0.59. For trifluoroacetic. So I can also adjust the acidity of this structure by putting more electronegative things on the back, which is going to pull that